Hello everyone. In the last class, we introduced the classification of transformers and the nameplate of transformers. Today, we will talk about the basic structure of transformers. The picture shows the structure of an oil-immersed power transformer in a schematic diagram. There are many types of transformers, but each has its own structural characteristics. But their basic structures are similar. Core, winding, insulation, and rated components are common in this section. We take the oil-immersed distribution transformer as an example for a brief introduction. Below are its basic components. The core body includes the core and windings. Other parts include the oil tank, transformer oil conservator, also called the oil pillow, moisture absorber, also called the breather, safety channel or pressure relief valve, gas relay, insulation bushing, tap changer, cooling devices, etc. The core is both the magnetic circuit and the mechanical framework of the transformer. The core is composed of the core column and the yoke. These two parts, the coil is installed on the core column. The yoke makes the entire magnetic circuit a closed magnetic circuit. According to the core structure, transformers can be classified into core type and shell type. Because the core type structure is relatively simple, and the assembly of the coils and insulation are easier. Therefore, domestic power transformers all use core-type structures. To reduce hysteresis and eddy current losses in the core material mostly uses cold-rolled silicon steel sheets with a thickness of 0.23 to 0.35 millimeters, coated with varnish to reduce the gaps between the sheets, to reduce magnetizing current. When laminating, a staggered stacking method is used. That is, the joints of the upper and lower layers are staggered. In large transformers, high magnetic permeability and low loss cold-rolled silicon steel sheets are used with slanted cut sheets to reduce additional losses at the corners. The cross-sectional shape of the core column in small transformers can be square or rectangle. In large capacity transformers, to fully utilize the inner circular space of the coil, a stepped cross-section is generally used. When the diameter of the core column is greater than 0.38 meter, an oil passage is left in the middle to improve the cooling of the core. The cross-section of the yoke can be rectangular or stepped. The area of the yoke is generally 5% to 10% larger than the core column to reduce magnetizing current and core losses. The core and its metal components and the alternating magnetic field of the coil, under the influence due to different positions, induced electrical motive forces also differ, thus causing discharge phenomena. To prevent core discharge, the core and its metal structural parts must be reliably grounded. The core is made up of many silicon steel sheets, laminated together. If the core has two or more grounding points, then when the magnetic flux in the core changes, it will generate an induced circulating current in the grounding circuit. Therefore, the core can only have a single point grounding. The winding is the electrical part of the transformer. Generally, insulated copper wire or aluminum wire is used for winding. From the relative position between the high and low voltage windings, the windings of the transformer can be classified into concentric and overlapping types. Concentric type high and low voltage windings are concentrically mounted on the core column. For insulation purposes, the low voltage winding is generally placed close to the core, and the high voltage winding is placed outside the low voltage winding. Due to its simple structure and easy manufacturing, domestic power transformers all use this structure. Concentric windings can be further divided into cylindrical, helical, continuous, and interleaved types as basic forms. In recent years, the high voltage windings of domestic large capacity transformers all use interleaved continuous windings to improve the initial potential distribution under atmospheric overvoltage conditions on the windings to prevent winding insulation from being broken down during overvoltage. Overlapping type high and low voltage windings are placed in overlapping positions and are mainly used for low voltage, high current welding, furnace transformers, and shell type transformers. The oil tank is welded from steel plates. The oil tank of large transformers is generally made in bell type. Medium and small transformers are generally cylindrical. To increase the cooling area, there are generally cooling tubes installed on the oil tank walls. The oil tank acts as the transformer housing, providing cooling, heat dissipation, and production. Transformer oil in oil immersed transformers. Transformer oil is both an insulating medium and a cooling medium. Transformer oil requires high dielectric strength, high flash point, low pour point, low dust and impurities, and low moisture content. Transformer oil, even a small amount of moisture, can greatly reduce the insulation strength. Oil conservator, oil pillow, to keep the transformer oil in good condition for a long time. An oil conservator is usually installed on top of the transformer oil tank. The oil conservator is cylindrical in shape. On one hand, it can regulate the oil volume, providing room for the thermal expansion and contraction of the transformer oil. On the other hand, it can reduce the contact area of the oil with air, thus reducing moisture absorption and oxidation. The oil conservator has a moisture absorber installed on top. Air must pass through the moisture absorber before entering the oil conservator. Moisture absorber breather contains silica gel. The insulating oil in the oil conservator is connected to the atmosphere through the moisture absorber. The decedent absorbs moisture from the air to maintain good insulation performance of the internal windings of the transformer. Silica gel discoloration and deterioration can easily cause blockage. Safety channel, explosion-proof tube, or pressure relief valve. The safety channel is also called the explosion-proof tube. When a short circuit occurs inside the transformer, the oil rapidly decomposes and generates a large amount of gas. At this time, the internal pressure of the transformer increases sharply, which may damage the oil tank and even cause an explosion. To avoid this, an explosion-proof tube is installed on the top cover of the transformer. The outer end of the explosion-proof tube is sealed with a glass sheet. When the internal pressure of the transformer suddenly increases, the oil rises along the tube, breaking the glass sheet and spraying oil outside, preventing the oil tank from exploding. Gas relay installed on the connection pipe between the oil tank and oil pillow. It is one of the main protections for the transformer. When a fault occurs inside the transformer, due to insulation breakdown, the gas-produced forces the gas relay contacts to close, sending a signal to the control room. Operating personnel immediately take measures to eliminate the fault or trip the circuit breaker automatically to prevent the accident from escalating further. Insulation bushing. Fix the lead wires and ensure insulation between the lead wires and between the lead wires and the oil tank. The structure of the insulation bushing depends on the voltage level. For voltage below 10 kilovolts, solid porcelain bushings are used. For 10 to 35 kilovolts, hollow air-filled or oil-filled bushings are used. For 110 kilovolts and above, capacitive bushings are used to increase surface discharge distance. The outer part of the high voltage bushing is made in a multi-umbrella shape. The higher the voltage, the more layers of the umbrella shape. Voltage regulation device, tap changer. The transformer uses the tap changer to regulate voltage. The tap changer is generally installed on the high voltage side. By changing the number of turns of the winding to achieve step voltage regulation. The voltage regulation method includes the following two types. No-load voltage regulation, also known as off-load voltage regulation. When using this method, the tap changer must be switched. When the transformer is not energized, the tap changer used is called the off-load tap changer. Unload voltage regulation, that is, the tap changer is switched when the transformer is under load. The tap changer used is called the unload tap changer. Cooling device controls the temperature rise of the transformer. According to different cooling methods, it can be divided into oil-immersed self-cooling, oil-immersed air cooling, and forced oil circulation oil-immersed self-cooling. Relies on the convection of transformer oil. Heat is dissipated through the radiator. The radiator has a large contact surface with the air. Heat is easily dissipated, thus accelerating the cooling of the transformer oil. The cooled oil returns to the oil tank to cool the core and windings. This cycle repeats so that the temperature of the windings and core will not rise. To speed up the cooling of the oil, fans are installed on the radiator. This cooling method is called forced cooling. Currently, large power transformers, this cooling method involves installing a separate cooling device outside the transformer body. The oil in the oil tank is forced to circulate through the cooler by oil pumps. The heat from the transformer oil is dissipated through the cooler tube's wall. The cooled oil after cooling is pumped back into the transformer. The temperature of the oil is reduced. This cooling method has a good cooling effect on the transformer. After class thinking question, please mark the positions in the diagram below. Oil conservator, high voltage bushing, gas relay, air cooling, radiator, moisture absorber. Today, our class ends here. Thank you for watching.